This video is an introduction to the Constraint Programming Solver in Julia series on my blog Open Sources. And it's part 1 to part 8 of the blog, shortly explained here in a video, so you don't have to read all the details in the blog. But if you want to know some more details, you have to check out the blog. You should definitely do it. So what is constraint programming about, and why do you want to have a solver in it? So a constraint programming solver is a general solver for many different applications. For example, it's kind of similar to a mixed integer problem solver, which if you have a problem which can be constructed as a mixed integer problem, you can solve it with any mixed integer solver. It's not specialized for one problem, it's specialized for a kind of problems. And it's the same for constraint programming solvers. So we can solve simple puzzles like Sudoku 8 queens problems or variants of Sudoku like killer Sudoku, which I do in the blog as well. So one big thing is, for example, scheduling problems, so timetable problems, or stuff like that. So if you want to create a timetable for university or for workers in a company, you can use constraint programming as well. And another quite famous example, I would say, is graph coloring. So if you have a map of some countries or something else and you want to color it in a way, so you want to visualize it and you want to color it in a way that countries which have a border don't have the same color. You can use constraint programming as well, and we will do that later in the series as well. It's probably the next part. Today I want to show you a recap basically of the currently 8 blog posts on the series of how to build a constraint solver from scratch in Julia. So what I want to do today is basically go through the code and explain the overall structure again, which might be a little bit easy if you can see the code and not just reading the blog post. And yeah, so just start. So I have here the basic structure is having some benchmark folder, folders which are in the git ignore like literature and GIFs. So then we have the source folder and the test folder having some visualizations, which has a visualization script and the images. So something like this, which I create with this file over here. The license folder, the license file, project and manifest toml, and just the README. So in the test folder, I have always a current.jl file, which basically is a file which is consistent over all branches I have. So it's just for running some tests easily. That's why it's not in the that's why it's in the git ignore file as well. And here you can see the basic structure of the user interface at the moment is we initialize the constraint solver, which is CS here. And we have the 9x9 Sudoku grid over here. And then I check whether there is a 0 in the field. Then we just have the variable 1 to 9, or the range from 1 to 9. Otherwise, we fix it to the value which is set. Currently have a plotting function here, so you can see the Sudoku on the right hand side. Then we have the add Sudoku constraint function, which creates from one row or from one here from row and here one column the variables and flattens it out, because this is 2-dimensional and this is a one-dimensional array. and gives it to the all different constraint, which we will have a look in a second. Then we have the block structure, so the block row, the block column, which is basically the same thing again. And if we have a look in here, which unfortunately can't find, so to the source file, so we have here the all different file, and it creates a basic constraint. So a basic constraint means it has an index, it has a function, so this is the function name of the constraint, the indices, which the constraints is working on, so basically the variables, and the possible values. So in Sudoku it's always 1 to 9, and yeah, we don't want to always set everything at the beginning, so we can set it later on, like the possible values will be created later. And let's go back. So here we call the all different function, which will be this one later on. And we have the indices of the variables. And then we return the constraint. So we go to this one. Then we can go to the add constraint function. And here we create the index, push it to our constraints, set the possible values, here always 1 to 9 again, and then set the subscription. So the way is, if we want to prune later on, so if we set the 8 in the corner you can see in the picture, we want to prune again the first row, the second column, and the first box. So that's that part. Now, if we go back, after we add the constraints, we call the solve. So if we go to solve, we check first whether everything is fixed, because then we're solved everything. Then set in all different and simplify is for the killer Sudoku later. So and set in all different, we basically check which part, or if the whole constraint is also part of an all different constraint, because that might be reasonable to know for the sum constraint, for example. And in simplify, we can also check whether we have an all different constraint and a sum constraint, because the all different constraints in Sudoku, for example, if we add up 1 to 9, we get to 45. So if every number we have is also used, we can make a sum constraint out of it, and maybe can use that for adding other sum constraints, which might simplify the model. So let's talk about pruning. So the first thing is that we call every constraint which we have, which is done in here. So this constraint function is we call the all different constraint with our basic constraint we have, and get a result, which is the constraint output. The constraint output holds information of how many values got pruned in each index, because later we might want to reverse the pruning step. Here it's not important because it's not in backtracking, but inside backtracking we want to be able to reverse pruning. Okay, we also want to return this solution, or whether it's infeasible, as fast as possible during the process. So we check if one constraint already said it's infeasible, we can return infeasible. We also check whether everything is fixed after this first step, which might not often be the case, but anyways. And then we do a prune step. So we saved the constraint outputs and the constraints here, or like the constraint outputs, and we used every constraint. So in if we go to pruning, the way is if something has changed, like for example, again, we set the 8, then we want to call the functions again. So the first row, second column, and first block. But if something else in the first row changed as well, we don't want to call it twice because nothing changed in between. So we only want to call it once. It's the important part. Later we go over all the constraints which we want to call again, and then we call them. If it's infeasible, we set feasible to false, break out of it, and can return it later. Otherwise, if something is changed again, so this is this part of the constraint output, we want to know whether we call that function later on anyways, because then we don't have to push it again into our list. Otherwise, we push it into our list, and this gets run over and over again until nothing changed anymore or something is infeasible. And then we return which constraints we used. So here we push everything if it's not in pre-backtrack, because then we don't need it, and to the constraints outputs, which we only need to for reverse pruning later. But at the moment we are before backtrack. So if we go back to solve, this is that part. And if now something is infeasible, we return infeasible because everything is just pruned, no backtracking involved so far. If we use backtracking, so if backtracking is allowed and it's not solved yet, we use backtracking, set the information backtrack to true, and call the backtrack function. When we are in the backtrack function, okay, let's close this one. We want to get a weak index. So that means if we have 2 cells, for example, and one cell has all possibilities 1 to 9, and the other ones got pruned already, so it only has the possibility 5 and 7. We want to use the 5 and 7 one, because if we can easily prune the 5 away, so that we know, okay, if we set the 5, it's getting infeasible, we know that it is the 7. But if we just know the 1 is infeasible and the other one, we still have 8 other possibilities to check. And now we have the following structure. We want to do backtracking without recursion. So first of all, we check for the index what we have, so which values are possible. Then we create a backtracking object, which you can see on the right hand side. And we set our variable index, we set our possible value index to 0 and increase it later. So if we have 5 and 7, we want to start with 5. Then we prune 5 and maybe set another value if it's not infeasible or not solved yet, and so on. But if it gets infeasible, we want to increase the counter again here to the 7 and then check the 7. That's why we have the possible value index. And then the possible values we just got, we save it there and fill in the backtracking vector, which is basically kind of a queue of the tree structure of our backtracking tree, basically, which we don't save as a tree. Then we get the first backtracking object, which is the one we just created, increase the p-value index, and if the prune part of the backtracking object is defined, we know that we pruned something already, so we reverse the pruning, which we don't have to do in the first step. Okay, now we check whether we tried every value already, and if we did, we have to revert the last pointer and the first pointer and set the minimum and maximum value of the current variable. This is more explained in the variable section of the blog post. So it's important to know how the variable inside works. And yeah, you can read more about that there. And now we check whether the value is still possible. So we have also, for every constraint, we don't only have the pruning part of the function of the constraint, but also just check whether if we set one value, if it's still possible, which is the lower part here. Now, if this is not feasible, we can just return. Otherwise, we fix that value and then we prune. If it's not feasible, we reverse the pruning step. Otherwise, we try to prune even further. If it's then not feasible, we reverse the pruning and continue to the next one. Otherwise, we get a weak index again. If there is no weak index, we know that every variable is fixed. So we can return solved and increase the backtrack counter. And then for reverse pruning, we always need to say what we pruned. So pruned below. And this is used for reverse pruning, which I'll explain in a second. So we have two different versions of reverse pruning, one which uses the constraints and constraint outputs if we don't have the backtracking object yet, and the other one uses the backtracking object. But they basically do the same thing. They call the single reverse pruning function. So it prunes a single variable back, or reverse the pruning of a single variable. And what it's done there is if we pruned something, then in the variable section, which you can see on the right hand side, we change the last pointer a bit to the left, and now we revert that change back to the right again, which is the red line on the right. Okay, so for the last part of the series of this video, I want to show you how to add an extra constraint. So we create the most basic constraint that exists. It's the equal constraint. So whenever a variable a equals to 5, for example, then variable b equals to 5 as well if variable a equals to variable b. So let's start. So first of all, we go to the include and call it equal. Then we create an equal.jl file, and we need 3 functions. So one which creates the constraint, one which prunes, and one which checks whether it's feasible if we set it. So let's start with the most basic one. So we can use the same basic constraint as well here, because we don't need a right hand side or stuff like that. We can, so basically we don't just have a equals b, we have all these variables equal one integer. So we have a vector as well. So looks like this. So the next part would be this function, which actually prunes. So it should be fine. So we have a basic constraint here as well. Then we have changed, so which part changed, pruned, and pruned below. This is for the reverse backtracking later on. And we can get the fixed variables and the unfixed indices. So here we basically get the set. So if the length of the set is bigger than 1, then we can say, okay, the problem is infeasible, because there is only be allowed to be one value. Otherwise, if the set has the length 0, so nothing is fixed, we can return, okay, it's feasible, but we can't prune. And otherwise, prune set all variables to fixed value. So for e in unfixed indices, has the index which is indices I, and then we call the fix function, which it returns feasible, pruned below, and pruned above. And we want to fix the variable at position index to fixed. Well, it's the first one because they are all the same. And now, if not feasible, we can return false. And yeah, could also warn, but it's not that important. So and then we set changed of index to true and pruned of I. So this is the local index basically, and this one is the global one, to pruned above. Yep, and pruned below I to pruned below. And return this one. Okay, and the last part, is to check whether if we set something, it is actually feasible. So this is when we set a variable to a value in backtracking. So if all are set to the value we have here, or the value is not fixed, or the variable is not fixed. And then we basically just have to create a file, which I just call equal. You can load the terminal already. And then we have our model, and then we have our variables, which is an array of CS variable. Let's just take 2 of them, and the next thing is we set variables 1 equals CS at var. So this is the range, and we fix the second one to 2, and then we create our constraints. Of CS equal. So later we want to write variables 1 equals variables 2, but let's do this one first, because the other one is not implemented yet. And then we have cs.solve the model, and we get a status. and variable 1 has the value cs value of variables 1 and 2 as 2. Oh, it's not called graph color, but equal. Oh, this is of course fix it to 2. What is the name? Oh, okay. Add variable like this. And now that takes a while for the first time, but when you run it again, it's obviously quite fast. We can also do some benchmarking if we want. Oh, I shouldn't return it. Okay. That's why I normally have if not benchmark. Okay. Yeah. The last part I can show you is if we want to write it like this. We currently get, okay, there is no add constraint with bool, so this one is normally a boolean because it's just comparing these two, but so we can kind of copy this one to equal. So instead of using this to construct the constraint, we can use compare variable with variable and create a basic constraint. Instead, we call equal again the indices are x point index and y dot index. And then we have the same thing again. All right, that's it for today, and see you on the blog.